driverless F1 car is a different kind of racing. Every brake, corner, and acceleration is calculated from thousands of data points each second. As Lewis Hamilton says, F1 is about instinct and feel. So let's just say the machine can't feel, but it can react faster and never tire. However, the real question is how close it can get to a human driver, and what an F1 car can really do without anyone inside. Modern Formula One cars are some of the most advanced racing machines in the world. They produce immense power, reach extreme speeds, and rely on highly tuned aerodynamics and tires to stay on the track. The cars we see on race weekends now use 1.6-liter turbo hybrid V6 engines. In race mode, these engines produce roughly 850 horsepower, and with hybrid boosts, they can briefly hit about 1,000 horsepower. The chassis is made from carbon fiber composites, giving the car extreme strength while keeping the weight around 795 kilograms with fuel and driver. The aerodynamics produce over 2,000 kilograms of downforce at top speed, pressing the car to the track for better grip in corners. The brakes are carbon discs capable of slowing the car from 200 miles per hour to a standstill in less than 4 seconds. Tires are made for maximum grip, with temperature ranges between 90 to 110 degrees Celsius being ideal for race conditions. Every part of the car works together to create a machine that is reactive and fast. Current F1 drivers are well aware of the complexity. Lewis Hamilton has said, "The car talks to you. You have to listen. Every lap is different, and you react to what it's telling you." And then Max Verstappen adds, "It's not just about going fast. The car, the tires, the track, the strategy, you have to manage all at once. It's like solving a puzzle while driving at 200 miles per hour. If we take the driver out, all of the car's original performance remains. The engine still produces its full horsepower. The aerodynamics push the car down. The brakes and suspension operate as designed. Tires provide grip, and the mechanical systems still respond. What changes is the control layer. Everything the human driver does instinctively must now be handled by software, sensors, and actuators. Steering, braking, throttle modulation, energy recovery deployment, gear shifts, and responses to changing track conditions all need automation. High-speed automated technology. Automated technology in racing is already reaching impressive levels. In 2025, a fully automated Maserati MC20 reached 197.7 miles per hour on a straight track at the Indy Autonomous Challenge. The car used cameras, radar, LiDAR, and inertial sensors to measure position, speed, orientation, and track limits. Control software processed this data multiple times per second and drove the car with no human input. Speeds of 273 kilometers per hour were documented in race simulations, showing that automated stacks can operate safely and repeatedly under some high-speed conditions. This demonstrates the potential. The hardware is capable, and software is reaching levels where some aspects of human control can be replicated or exceeded. The same technology stack has also been used in automated racing competitions, where cars navigate high-speed circuits, overtake other vehicles, and manage braking and acceleration safely. This demonstrates that sensors, control algorithms, and actuators can manage a high-performance vehicle at speeds approaching those of sports cars. And really fast, guys. If you've ever dreamed of feeling like you're actually driving a Formula One car, or even testing your own setup safely before hitting the track, you're going to love this next part. Testing car setups, learning the limits of speed, or practicing high-performance driving is expensive, risky, and sometimes impossible in real life. Tracks cost money, crashes can happen, and without experience, it's easy to make mistakes. Now, to make a driverless F1 car, all of the existing mechanical and aerodynamic systems would stay, but an advanced control system would take over. Sensors around the car detect track boundaries, tire slip, surface temperature, and mechanical loads. Inertial measurement units track acceleration, pitch, and yaw. Tires are monitored for wear, temperature, and pressure. Suspension movement, downforce, and mechanical stresses are measured in real time. A high-speed computer fuses all of this information and commands the actuators, steering, braking, throttle, and potentially active suspension or energy deployment systems. Even with this system, racing is extremely complex. F1 drivers deal with unpredictable tire behavior, weather changes, mechanical vibrations, debris, and the actions of 19 other drivers on the track. Human senses detect subtle changes that sensors can struggle to identify. Sebastian Vettel said, "We make decisions instinctively. You sense the grip, the downforce, the tires, and adjust. Software has to interpret all of that in real time, which is incredibly hard. Where a driverless F1 car could excel is in consistency. Machines do not tire, they do not overreact. Reaction times can be faster than human reflexes. Automated systems can maintain ideal braking points, throttle application, and energy deployment over long runs without degradation. For example, tire management could theoretically be optimized perfectly, preventing overuse or overheating during long stints. But challenges remain. Tires degrade differently depending on track temperature, grip, and debris. Aerodynamic loads change as cars slipstream or overtake, shifting downforce and balance. Mechanical feedback from suspension and brakes is continuous and complex. Humans adjust instinctively to these changes, while a machine must rely on pre-programmed responses and real-time calculations. Even small delays or errors in sensor fusion can lead to understeer, oversteer, or mechanical overloading. Corners are more complicated. Tires wear unevenly, track temperatures change, and debris can appear suddenly. Human drivers feel subtle changes through pedals, steering, and seat vibrations. Autonomous systems rely on tire sensors, wheel speed, and temperature readings. They react quickly, but perfect performance in every condition is extremely hard. Overtaking relies heavily on human judgment. Drivers anticipate opponents, pressure them, and choose precise moments to move. Max Verstappen said, "Racing is reading the other driver." Machines don't read the car in the same way. Autonomous cars detect other vehicles using cameras, radar, and LiDAR, and plan paths. But split-second decisions in crowded corners are a major challenge. Real-world conditions remain a challenge. Rain, changing grip, debris, mechanical failures, and interactions with other cars introduce variability. Humans interpret subtle cues and adapt. Machines can use sensors and predictive algorithms, but may be overly cautious or fail to react optimally. Yet F1 is not only about straight-line speed. Strategic decision-making is vital. Drivers manage tire degradation, decide when to use hybrid boost, overtake, defend position, and adjust to incidents. Lando Norris has said, "Racing is a mix of strategy and skill. It's about knowing the track, the car, and the other drivers. Timing, patience, and aggression all matter." Replacing these decisions with software means creating predictive models for dynamic, unpredictable situations. This adds complexity and risk. Energy recovery adds another layer. F1 cars recover energy under braking and redeploy it under acceleration. Human drivers balance this with tire management, braking bias, and traction control. A machine can execute the calculation perfectly, but may lack the instinct to adjust in unusual circumstances. The Ferrari SF23's hybrid unit, for example, can deploy around 120 kilowatts of recovered energy, but timing that deployment in traffic is critical. A driverless system would need advanced prediction algorithms for multi-car dynamics, adding processing load and potential delays. Even with these challenges, automated racing teaches us a lot. Current driverless systems show that high-speed control, obstacle avoidance, and energy management are possible. Sensor fusion allows precise positioning, while high-speed path planning enables safe overtaking. Redundant systems ensure failures can be handled without total loss of control. These developments could be applied to a full-scale F1 chassis, although at significant engineering cost. What we know for sure is that the mechanical foundation of an F1 car is already capable of incredible speed, and software-controlled vehicles can handle extreme velocities in controlled settings. This combination makes the idea of a driverless F1 car technically feasible. The main limits are the unpredictable nature of racing, tire wear, weather, mechanical shifts, and other drivers' behavior. Autonomous cars have demonstrated high-speed control. In the Indy Autonomous Challenge, full-size cars reached 270 kilometers per hour, overtook other vehicles, and kept racing lines without human input. These were controlled environments, but they proved that the mechanical and software foundation exists. F1 cars, however, are faster and face tighter corners, higher G-forces, and denser traffic. A Formula One car without a driver keeps the same engine, brakes, tires, suspension, and aerodynamics. The difference is that steering, throttle, braking, energy recovery, and gear changes are handled by software and sensors. Machines do not tire or make small errors from distraction, so lap consistency is extremely high. On straights, A driverless car can use full power efficiently and manage energy deployment with millisecond precision. George Russell has said, "Energy management is one of the hardest parts of driving an F1 car. If a car could do that perfectly every lap, it would be a tough challenge for a human." The hybrid systems, which recover and deploy energy under braking, can be used optimally every lap with software. Tire management is critical. Pirelli tires change grip with heat, wear, and track surface. Humans feel these changes and adjust instantly. Carlos Sainz said, "You feel the car's behavior through the seat and pedals. Tires tell you what to do before telemetry shows it." Autonomous systems use sensors to detect slip and temperature, but must translate raw data into safe, fast driving, which is difficult over an entire race. Aerodynamics adds more complexity. Downforce changes with speed, track layout, and nearby cars. Wake turbulence affects balance. Human drivers feel this instinctively, while machines calculate it in real time. Christian Horner said, "Human drivers can cope with turbulence instinctively. Coding that into software is possible, but it's not easy." Strategy is another challenge. Drivers decide when to pit, when to push, conserve energy, and manage tires. Lando Norris explained, "Strategy is part of the game. Sometimes you hold back to save tires or energy. Other times, you push everything to win a position." Autonomous systems can calculate ideal strategies using data, but unpredictable events like crashes or weather can disrupt plans. Energy recovery is fully controllable by machines. The hybrid system recovers energy under braking and redeploys it under acceleration for up to 120 kilowatts. Software can manage this precisely, but errors could cost time or cause mechanical issues if models fail in unusual situations. Hybrid approaches are likely first. AI can help humans manage energy, tires, and strategy. This is already part of F1, where telemetry informs drivers in real time. Combining machine precision with human instincts improves performance while keeping racing exciting. Driverless F1 cars are possible. Mechanical performance and sensor systems exist. Software can control braking, steering, throttle, and energy. Machines can be faster in consistent laps, precise with energy and tire management, and gather data humans cannot. Human drivers provide instinct, experience, and intuition. Racing involves reacting to competitors and unpredictable conditions. Alonso said, "The car talks to you, and you respond." That connection is what makes racing exciting. Hamilton added, "The human element is emotional, instinctive, and critical to the sport. Software cannot feel the car or competitors the way humans do." Driverless F1 could exist as a separate championship. Teams could compete on software, sensors, and strategy. It would test engineering rather than human skill. Real-world autonomous racing proves high speed, multi-lap operation is achievable. Safety, unpredictability, and fan acceptance remain challenges. The future may blend humans and AI. AI can manage tires, energy, and predictive strategy, assisting drivers while retaining human instinct. Fully autonomous F1 races might be separate events focused on precision and engineering, not human skill. This approach could advance technology and safety while keeping traditional F1 intact. A driverless F1 car is possible, but it couldn't race in today's F1 without changes. Modern rules, safety, and track challenges mean it would need separate events, simulator runs, or test laps to show its potential safely. The question isn't just, can it be done, but how far can it go? Autonomous F1 could open a new chapter in racing, and everyone would be watching. Let us know what you think in the comments, and don't forget to like and subscribe.